Hello and welcome to my presentation here at Bodo's Wide Bandgap event. My name is Carsten Schreiter. I'm Product Marketing Manager at Semikron Danfoss, and today I will speak about the benefits of using silicon carbide in general purpose motor drives. I begin with a few facts about Semikron Danfoss. I think it's well known by now. In August 2022, Semikron and Danfoss Silicon Power joined forces and merged, and the newly formed company is called Semikron Danfoss. With 3,500 employees, we now form the largest chip-independent manufacturer of power modules, and this merge also expands our presence in all areas, meaning with 10 factories in 8 countries and 28 sites on 5 continents, we're now closer to our customers than ever before. We're innovation driven. We hold over 600 patents, and 15% of our employees are in research and development. Furthermore, we also plan to invest significantly in innovation, technology, and the capacity to enable our customers' future growth plans. Part of that, for sure, is the silicon carbide technology, which I will speak about today. Let's now come to the main topic of my presentation and take a look at how AC motor drives can benefit from silicon carbide. Silicon carbide has been around for a while now, and it has undoubtedly contributed a lot to improving the efficiency and many power conversion applications. I'm talking, for example, about solar power conversion applications, energy storage, EV charging, the electric vehicles itself, but there are also many others. If we now, however, look at the industrial motor drives side, then we will find that except for some very special applications, the silicon carbide has not gained a similar level of acceptance here. Now, why is that? Well, one of the reasons is for sure the cost of silicon carbide, but there are also some technical reasons. For instance, that in the most motor drives applications, the motor windings, but also the cabling, set strict limits for the switching frequency and also the voltage rise time. That means that the main benefit of silicon carbide, the fast switching with low losses, could only be used with additional effort for filtering. On top of that, each motor drive typically requires a certain level of short circuit withstand capability, and exactly that has been one of the weak points of silicon carbide in the past. Now, developments are fast in the silicon carbide world, and especially with the latest generation of chips, we truly believe that it makes sense to seriously consider silicon carbide also for motor drives. Why? I will tell you on the following slides. I will show how power modules with the latest silicon carbide chips properly used in motor drives can on one hand greatly contribute to energy savings and with that also to decarbonization of the industry, and how they on the other hand give drive designers totally new degrees of freedom in designing their drives. In the presentation, I will concentrate on what can be achieved without the ultra-fast switching. So, if you will, we are looking at a race car here, which is on bicycle tires, but you will also see that it really can make sense to do so. So first, let's recall the basic parameters or the basic properties of silicon carbide technology, and then look at how we can utilize it in a beneficial way in the drives. The first thing I want to highlight here is the forward voltage drop of a silicon carbide MOSFET. Unlike in an IGBT, the voltage drop here depends on the load current, and that means that if we are at partial load, and that's where the majority of all drives spend most of their time, then we have a much lower voltage drop compared to an IGBT. And this lower voltage drop affects the losses and also the efficiency in a positive way. To what degree, we will see in a minute. We can also say that silicon carbide can be switched much faster than IGBTs, and thereby the switching losses can be reduced. Silicon carbide also has a 2 to 3 times better thermal conductivity when we compare it to silicon, and this improves the heat spreading and also means that we, in the end, don't have any hotspots in the chips. Another important point is that if we use silicon carbide MOSFETs in a motor drive, then typically the embedded body diode serves as a freewheeling diode during the dead time. This body diode acts as a bipolar device, but compared to a pin diode, standard pin diode, it has a much faster recovery, thus the recovery losses are much lower. Additionally, when we use the body diode, the temperature swing in the device is lower than with separate switch and freewheeling diode, and this has a positive impact on power cycling. Last but absolutely crucial for motor drives, the short circuit withstand capability. With IGBTs, 8 to 10 microseconds of short circuit withstand capability are kind of state of the art. And silicon carbide has been a bit weak here, but the good news is that with the latest generation of silicon carbide chips that we use in our power modules, we can also provide up to 2 microseconds of short circuit withstand capability. And that means that other than former generations of silicon carbide chips, the newer ones are very attractive for usage in motor drives. Let's now see how those benefits of silicon carbide translate into better drives and into higher degree of freedom in design. I'm starting with a great potential in energy savings, actually with a few interesting facts about energy consumption by motors and drives. That is just to better understand the scope of it. The International Energy Agency reports that 20% of the world's energy consumption is electrical energy. 50% of the globally used electrical energy is consumed by electrical motors, and now 70% of that is used in the industry, where the majority of motors run fans, pumps, and compressors. These are often variable torque applications that run 24/7, and most of that in low or medium load, only rarely at full load. So looking at those figures, it also becomes clear that if we want to conserve energy and decarbonize the industry, these applications make a good starting point. Of course, changing them from traditional valve or throttle control to speed control with a motor drive massively contributes to energy savings, but it can even be more if you manage to push out the efficiency of any part in the system, and that means also the drives. And this is where silicon carbide enters the stage. To evaluate the energy saving potential of silicon carbide, we simulated a 15 kilowatt pump application here. In a pump application, the torque or the motor current is proportional to the square of the speed, means at 75% of the speed we have only half the load current, and 50% of the speed we have only 25% of the load current or torque, and so forth. We did the simulation here with a power module that was once equipped with a generation 7 IGBT, and on the other side equipped with the latest generation silicon carbide MOSFET chip. We compared the watt losses and the efficiency on the module here, and switching conditions were 5 kilowatt per microseconds and 5 kilohertz, so pretty standard values in the drives world. The result we see on the chart on the right. The solid lines represent watt losses, dotted lines efficiency, gray is for silicon, red is silicon carbide. And you can easily see that the silicon carbide shows remarkably lower losses in the whole speed range. If you look at 40 to 80% speed, for instance, which is a totally typical speed range for pumps in operation, then we have a reduction of 62 to 54% in the watt losses. And in the same range, the energy efficiency or the efficiency of the module improves by up to 1.7%. That is quite impressive and clearly demonstrates the potential of savings in these variable torque applications. We also had a look at the expected lifetime here. A pump or a fan is usually a pretty steady load without big peaks, and also the fact that we use the body diode here leads us to a result where we can say that the expected lifetime in this application for both modules is comparable even without heavily oversizing the silicon carbide chip. That's another reason why we see silicon carbide as a perfect fit for variable torque drives. So now we looked at the module, but let's have a look at how that looks in a complete drive. Here we took a 15 kilowatt standard drive from Danfoss, which is already one of the most efficient standard drives you can find on the market, and we did the same simulation for this pump application as before. If you now look at the upper right chart, the left column is the losses with silicon, the right column shows the losses with silicon carbide, and we can clearly see that when we use silicon carbide, the losses of the drive at the rated speed of the pump would go down by 24%. If we talk about efficiency, then this is an improvement of 0.5%. If we look at the lower chart, we can see the whole speed range, and also here it becomes quite obvious that with silicon carbide at any operation point we have lower losses, and the drive efficiency can go up by 1% depending on the speed that the pump is working on. This might not sound like a lot, but if you remember that these fan and pump drives are often running 24/7, it becomes quite obvious that some savings can accumulate, and how that looks and what it means for the investment or the return on invest I will show on the next slides. For this return on invest example, I made a few assumptions. So silicon carbide naturally is more expensive than silicon, and it will most probably remain that way. So I said an end user who will also pay the energy bill, if that end user buys this 15 kilowatt drive, then he would probably pay roughly 90 to 100 euro more. The energy cost I set was 26 cents per kilowatt hour, and then I used this annual load profile, which you can see on the right. So I said at 10% of the time, the pump is not running at all. At 5%, it's running at 40% speed, and so forth. And if I then do the calculation for a year and accumulate the losses, what comes out is that with silicon carbide, those losses can be reduced by 55%, meaning 345 kilowatt hours or 172 kilogram of CO2 if we want to talk about decarbonization. It also means that this end user would save 92 euro in a year, and the payback time for this investment that he took would be less than a year or approximately a year. And it would be even shorter, and the savings would be higher with higher energy cost. So clearly shows that when we talk about silicon carbide, we also have to look at the application and not just look at the parts cost. Besides the way I described before, silicon carbide could also be used in different ways, and that I analyzed here. So in the upper example, I took the same packages as before, applied the same operation conditions, and then I tuned the heatsink dimension so that both run roughly at the same junction temperature, just to see how much I can reduce the size of the heatsink when I use silicon carbide. And the result is quite impressive if you look at the upper chart here. So it's 66% smaller heatsink that we need here. That means the weight of a drive could be reduced greatly. It also means lower overall material cost because the drive could be smaller, so less materials required, easier handling, then less shelf space, more drives on one pallet if you ship it, and so forth. So silicon carbide here can trigger a long chain of real benefits. One could also keep the size of the heatsink and reduce or even remove the forced cooling. There's really a number of possible options now. In the lower example, I kept the cooling at the same and wanted to see how much more current I could get out of an existing thermal design. And the result here is 19% more current or power. Means increasing power of an existing drive without touching the mechanical and thermal design too much becomes quite feasible. Summarizing, we can say, and I believe you don't disagree, that silicon carbide provides some really nice options for making better drives, especially variable torque drives, and that even without utilizing the super fast switching of silicon carbide. Designers now have more room to play. They can go for small size, they can go for high efficiency, they can go for higher power, or just set somewhere in between. Only one question remains: what product shall you choose? Well, of course, the correct answer is power modules from Semikron Danfoss, and here's why. We're the largest chip-independent manufacturer of power modules, and we've been packing IGBTs since more than 25 years. We've been packing silicon carbide chips since more than 15 years, so we really know what to do, and we know how to do it properly. We also have all the industry standard packages at hand, and we have the packaging technology to unleash the potential of silicon carbide. As an example, I have, for instance, the mini-skip sintered here, or the Semi-Top E, which has best-in-class thermal performance. We also have strategic alliances with all the major chip suppliers, and that gives us on one hand access to the newest silicon carbide technology, but on the other hand, by these alliances, we also can secure the supply, and that is something very important, as we have learned in the past years. And last but not least, we also have an experienced team with great application expertise that supports customers along their projects and beyond. So Semikron Danfoss can be the ultimate partner for your silicon carbide projects in drives or any other applications. With that said, I'm at the end of my presentation. If you want to challenge us in your next drive project with silicon carbide, or if you just want to discuss the topic a bit deeper, then let us know. Thanks for watching and have a great day.